everyone, I'm Angie Boggust, and today I'll be demonstrating shared interest, a methodology that leverages human annotation and AI saliency to explore model behavior. So I'd like to begin by imagining that we've just trained an image classification network and we'd like to evaluate its behavior. So we sample an image from our dataset. Here we have an image of a snowmobile, and we've highlighted the region containing the snowmobile in yellow. Our model correctly predicts this image as a snowmobile, and using our model and our favorite explanation method, we've created an explanation region shown in orange. So given this information, how would you feel about your model's behavior? Well, you might say that there's high overlap between the explanation and the ground truth regions. Thus, your model is relying on salient pixels to make its correct prediction, and you feel confident in your model's behavior. But you might want to take a look at a few more images. So if we sample from our dataset again, we might get these two images. Now again, we see there's high overlap between the explanation region and what we as humans believe are salient pixels to snowmobile, so our confidence is growing. But if we were to sample again and get these two images, we might not feel quite as confident. In the top image, we see a case where our model is relying on a snowmobile helmet to make the prediction of snowmobile, which is problematic because not every time a snowmobile helmet is in frame is there necessarily an image of a snowmobile. And in the bottom example, we see a case where the snowmobile is actually an insignificant portion of the image, which might be surprising if we didn't expect our dataset to contain images like this. And so the takeaway here is that selecting the right inputs to evaluate is challenging. We're dealing with large datasets, so we can't analyze every input. But depending on how we subsample, we may miss inputs that are most informative. And this is the problem that led us to develop shared interest, which is a method to explore model behavior by comparing ground truth regions to model explanations. And in this methodology, we began with a dataset that contains ground truth regions. Here, we use the ImageNet dataset, which contains object-level bounding box annotations, shown in yellow. However, you could apply this to other tasks and domains as long as there are these types of ground truth segmentations available in your dataset. Next, for every image or input in your dataset, we compute an explanation region. So here we compute a mask via lime, shown in orange. However, you could also plug and play other saliency methods as well. And then, using the overlap between the explanation region and the ground truth region, we score every image in the dataset. Here we use the intersection over union score, which is the number of pixels shared between the two regions divided by the number of pixels in either of the two regions. So this score is maximized when the ground truth region and explanation region are identical, and it's minimized when they are completely disjoint. And finally, using these scores, we sort and explore our dataset in order to find inputs that are informative. So for instance, in the top row, we show images that have low shared interest scores. And we see our snowmobile example from before immediately pops out with a score of 0. On the right-hand side, we see an example where the ground truth region and explanation regions are disjoint, but this time our model has latched on to a secondary object in the frame. Now, this may be surprising if we only expected our images to contain single objects. But looking at the high scores can also be informative. On the bottom left-hand side, we see an example where our model is right for almost exactly the right reasons. Our model is relying on pixels related to the trailer truck to make the prediction of trailer truck. And on the bottom right-hand side, we see an example where our model is looking at the right region, but it makes a prediction of motor scooter when the image has been labeled as moped. Now, this is likely a case of ambiguous labels, and that might be something we want to take into account in future iterations of our model. So just by sorting by this score, we're able to immediately gain insight into our model's behavior and unexpected features of our dataset. But to further prove this point, I'd like to walk through a case study on melanoma prediction. Here, we have images of lesions that have been labeled by dermatologists as either cancerous or benign, and we've trained a network to perform that same binary classification task. So we begin by looking at images with high scores that are labeled as malignant. And immediately we see that most of these images are being predicted correctly by our model. And we see high overlap between the explanation region and the lesion, which gives us confidence because we know dermatologists oftentimes use visual features to make a cancerous or benign prediction as well. So now we turn our attention to a more concerning case, where we have cancerous lesions that are being incorrectly classified as benign, and we look at those with the lowest scores. Here, we see oftentimes our model seems to be latching on to peripheral skin regions in order to make the classification of benign. And this doesn't happen in just one or two images, but it happens in a number of images, which is obviously very concerning since these are truly cancerous lesions. Finally, we take a look at benign lesions that are correctly classified, but have low shared interest scores. We see examples where, again, our model has latched on to peripheral skin regions, but as we scroll, we see that oftentimes there are these dermoscopic tools in frame that our model seems to be latching onto to make its prediction. We actually went back and looked at the data set and found that these dermoscopic tools only exist in benign images. So while the presence of this tool is sufficient to make a benign prediction, this obviously isn't going to generalize in a downstream task or if we were to deploy this in the real world. So here, just by looking and sorting these images in this way, we're able to gain insight into where our model succeeds, where our model fails, and unexpected features of our data set. So that's shared interest. Thank you so much. We have code, a demo, and an article on the link on the screen. I'm looking forward to answering any questions and demoing shared interest further in the live session. Thanks.
Angie, thank you so much for joining us for the live Q&A and for the fantastic demo that we just saw just now. I see that questions are already coming in from the participants on Zoom. So just as a quick reminder, you can either ask questions in Rocket Chat or you can join the Zoom call to raise your hand and ask the question live. But to kick things off, I was curious, the examples you showed in the last case study that you demonstrated showed some quite concerning issues where the wrong kind of features were used to make decisions with potentially life-threatening consequences. I was just curious how you see the follow-up from this. So what kinds of tools do you see, or what kinds of research directions do you view as crucial to address challenges like this?
Yeah, well, I think the big motivator for shared interest is mostly to make people aware that this is happening, to find ways to show people, these are the instances where your model is not performing well, and to really enable them to have the tools to go back and make the decisions that they feel are necessary in the model. Throughout our process, we had interviewed some machine learning experts, and a lot of the times, they were doing this sort of analysis, but querying single images or images they might have thought were hard, or sort of subsampling them in some way, query a few, compute your explanation, and sort of get a feel for it that way. And so I think what shared interest does is sort of give you a way to make sure you're looking at things that are informative, and then really enable you as the expert to go back and make the decisions that you feel are necessary to hopefully improve upon your model and prevent these very concerning cases from happening.
Fantastic, thank you for this. Next up, we have a question here on the call. Sami, would you like to ask your question live?
Yes, thanks. It was very interesting, and I was curious about that melanoma example that you showed on the first one. You can actually see when you order them by performance that of course, the size of the overlap matters, but the thing is, the size of the ground truth also differs depending on the image that you show, and that's going to have an impact if you limit the saliency area to some number. So do you have a specific cutoff threshold for the saliency area, or how do you do that?
Yeah, so for the saliency area that I showed in the example, we're using the top 30% of pixels activation to compute the mask that you see. You could imagine, setting that threshold however you want, or even, using other saliency methods as well. You could do the same thing for integrated gradients or pretty much any method you would like. But you're definitely right that the size of the ground truth area does affect the shared interest score. And that's something that we thought a lot about in terms of how to address it. I think we sort of fell on the side of, well, that is what's salient to the image, regardless of how big that area is. And so we didn't really address, or we sort of left it to that. If the snowmobile is this big in the image, it's this big in the image. Those are the salient pixels. But you could imagine taking that into account and scaling by the size of that as well.
Okay. Yeah, sounds good. Thanks.
Thank you.
Fantastic, thank you for that. I have another question. I think your demo mentions that the approach you're demoing here is agnostic to, for example, the modality of the data that you're looking at. But in the demo, you showed examples that are kind of most immediate and visual. So how should I imagine this, for example, looking at language or other modalities? How would that work?
Yeah, so we've been doing some work applying this to review data. So in particular, review data sets where the sort of salient words have been labeled. So it's so we're working on beer reviews, and it's, hoppy character is positive sentiment, and I don't know, disgusting taste is negative sentiment. So you can also imagine using this where you're sort of, in that case, your ground truth segmentation is really the words that have been characterized as, for instance, positive sentiment in this case. And your explanation would hopefully give you a similar set of words that it thinks are indicative of sentiment. And you can compute the overlap between those words as well. So that's an example of us using it on natural language. So as long as you have some sort of ground truth segmentation and you can generate some sort of explanation segmentation, you can compute the score.
Fantastic, thank you. We have another question from Rocket Chat, and I see Bilal is also here on the call. Bilal, would you like to unmute yourself and ask the question directly?
Yes, sure. Yeah, thank you, Katja, and thank you, Angie, for the really great demo. So, I mean, my question is that with some past experiences with working with IOU is that when your ground truth object is very small, then you anyway have smaller chance to really get it close match with the prediction, whereas like large objects spanning maybe 90% of the image have anyway very high chance to score a high IOU. Did you think that impact the kind of analysis you are doing, or it's anyhow not very significant?
Yeah, that's a great question. I totally agree that the size of the ground truth region definitely impacts the score. So in the examples I showed, we just used IOU, but in the interactive demo that we linked to, we have a variety of other scores that you can sort by as well. So for instance, we also generate 2 scores, one of which is ground truth coverage. So that is the amount of the explanation region that covers the ground truth area. And then we have the inverse, which is explanation coverage. So the amount of the ground truth area that's within the explanation. And you can sort of think about those slightly as analogous to precision recall. So those, you can sort of use those scores as well to highlight different aspects or sort through the images in a different way. So for instance, if you want to find examples where, your explanation is definitely taking into account all of the salient pixels, you can look at high ground truth coverage scores. Or, in the opposite case, if you want to find images where, you're using a subset of the salient pixels, you can look at high explanation coverage scores. And so we tried to add in additional metrics to sort of address the problem that you're asking about, but I agree that it'd be interesting to think more about metrics that are truly agnostic to the size of the ground truth region.
So yeah, thank you very much, Angie.
Thank you.
That's fantastic. Thank you for that. We do have time for 1 to 2 more quick questions. So if people have any additional questions, raise your hand or unmute yourself if you're on the call, or post the question in Rocket Chat. In the meantime, I'm curious in terms of the demo that you're presenting here. So for someone who has never tried this before, what would you recommend they get started with as they try out your demo?
Yeah. So if you actually go to the link, we have a brief article that sort of walks through a few examples. But in the demo, we have the melanoma study that I showed in the video, and we also have a subset of ImageNet that we have done this to as well on there. And so I guess to start, I would just suggest, exploring as serendipitously as you would like. But I think as you sort of start to get a feel for what the metrics are showing you, I think at least for me, I always start like generating hypotheses or finding things. You see an image that's really interesting and you can look for more images along the same lines. So I think the most interesting things to do are to select a metric. I think IOU is sort of the most natural, most intuitive one to start with, and just looking at the extremes. And immediately, for ImageNet, you'll find cases where the model is latching onto a secondary image in the frame. You'll find examples where, you'll also find examples where it does a really good job and it's looking at exactly the right image. And you can sort through and filter by the true class or the predicted class, or whether your model is correct or incorrect. And I always find myself starting to generate hypotheses about, oh, maybe this is a case where my model fails, so let me look at more images like this. Or let me see if this is a case where my model is relying on background features, so let me look at ground truth coverage and see if there's error rates there where, maybe you're looking at something salient in the background, like train tracks, but you're making the prediction of train. And so I think that is sort of a good way to explore the demo. I think ImageNet is something a lot of us are familiar with, so I think it's sort of an easy way to get familiar with the metrics and how this might be useful in your own work.
Fantastic, thank you. We have time for one last question, and for this one we will go to Rocket Chat. Annie Ruda is asking, in the case of transformer-based language models, given that the preference would be to evaluate the sentence as a whole, would the ground truth correspond to words or phrases in the sentence? Could you elaborate on that?
Yeah, I think that's a really interesting question, and something we haven't looked too much into. So I think that you could go either way. And like doing things both ways might lead to different and yet interesting insights. I can imagine that looking on a word level could be interesting to find, sort of word level, maybe that's redundant, but looking at the word level could help you find these sort of, I think it'd be interesting to compare the difference between the word shared interest scores and the phrase shared interest scores to sort of see if there's consistency or not. But I think that would be really interesting to take a look at and see what is most valuable or if they both have value.
Fantastic. Thank you so much, Angie, and thank you everyone for the great discussion. This concludes our first demo session. Thank you all so much for the fantastic demos that you have put together. I'm personally super excited to go and follow up with the many demos that are online and that will be continue to be online throughout the conference to play with some of the fantastic ideas that you have generated and that you're showcasing there. Also, please feel free to continue any discussions on the Rocket Chat. This will stay available and it's a great way to catch up. With that, thank you so much again to all demo presenters, and thank you so much for watching.